So far we've learned about all these different kinds of energy. We looked at kinetic energy, elastic potential energy, gravitational potential energy, and how to calculate them at any instant. We've also looked at trying to calculate the change in energy. If something goes from a relatively high position to a low position, what is the change in gravitational potential energy? Or if something changes its velocity, what is the change in kinetic energy? Well, now we're going to talk about, well, what happens to that energy when it changes? And we have the law of conservation of energy. In this case, we're going to be talking about the law of conservation of mechanical energy. So if we have an isolated system, so that means that like thermal energy and things can't move into and out of the system, then all mechanical energy is going to be conserved in that case. So energy is transferred from one form to another. There is going to be no loss of mechanical form. So if we look at that equation, it looks like a complicated equation, but really all it says is that all of the energies at the beginning of a scenario, so whatever potential energy and kinetic energy you have at the beginning of a scenario, has to be equivalent to the potential energies and kinetic energies you have at the end of the scenario when something has changed, right? So energy is converted from one form to another. And I'm going to do in this video an example of a problem where we're actually dropping something. Now, the law of conservation of total energy means energy is conserved completely, and this is when we don't have an isolated system. And in this case, we'd have to take into consideration like heat energy, frictional energy loss, but for our purposes, we're going to just treat all of the problems in this unit like we're an isolated system, and we're going to kind of ignore friction and the idea of heat loss in these instances. So let's go ahead and do an example of a conservation of energy problem where we're dropping something. Alright, so let's say I have, at the beginning of the semester, remember we started by learning about velocity and acceleration, and we said that there was a person standing on top of a cliff and they were going to drop a ball, and that ball was going to fall to the bottom of the cliff, and let's just say the cliff was 100 meters tall. Right? And we derived all these equations on how to figure out, you know, using acceleration due to gravity and the velocity initial at the top and the velocity at the bottom. But now we're going to use the idea of conservation of energy to solve this problem. So at the top, when you have a ball this high up, and let's just say the ball is 2 kilograms, right? And I have that ball and it's 100 meters up in the air. It has some gravitational potential energy stored, which is equivalent to mgh, right? Now, if I let the ball go, it's going to fall towards the bottom, and as it does this, it starts to move faster and faster and faster, and it starts to lose that gravitational potential energy, and because it's moving now, the gravitational potential energy is becoming kinetic energy. So that's our law of conservation of energy. Any energy that is lost as a result of potential energy now is being converted to kinetic energy. It's going somewhere. So if we were to drop the ball, we wanted to know, okay, well, how fast is the ball going down here? Well, once the ball has hit the ground, now the height is equal to 0, so the gravitational potential energy is 0. So whatever gravitational potential energy we started with at the top now has to be completely converted to kinetic energy. So down here, we're going to have kinetic energy, whereas up here, we would say the kinetic energy is 0 because the initial velocity was 0. So essentially, according to the law of conservation of energy, I can say that all the GPE, or gravitational potential energy, at the top is going to be converted to kinetic energy at the bottom. Right? So I can say the mgh at the top is equal to the 1/2 mv squared at the bottom. And I can figure out what the velocity is then at the bottom. And I know the ball has a mass of 2 kilograms, but if we look at the equation, we've got mass on both sides, so we don't even need to know that. So we would just do 10 for gravity times 100 for the height of the cliff is equal to 1/2 v squared. So if we solve for v, we get 10 times 100, oops, and then we're going to divide that by 0.5, and then we would just take the square root, sorry, this calculator is different, Alright, so it's 44.72 meters per second. So the velocity at the bottom will be 44.72 meters per second. Right? Now, if we look at the same idea, and let's say we wanted to figure out what is the velocity when we're 12 meters off the ground. Right? What's the velocity here? Now, when we did this with our constant acceleration equations, this was kind of a complicated problem, right? But now it's very simple. All we need to do is we need to figure out, well, what's the difference between the gravitational potential energy here and here, and we set that equal to whatever the kinetic energy of the ball is at that point. Because remember, that gravitational potential energy has just converted to kinetic energy. So we know that the difference in the height would be from 12 to 100, right? So that's 80 meters. So I know that the mgh is equal to the 1/2 mv squared. And in this case, the masses are going to cancel again. And I would just say 10 times 88, so that's the change in the gravitational potential energy there, is equal to 1/2 v squared. So 10 times 88 divided by 0.5, and then second square root second answer. Now we know that at that position it's going 41.95 meters per second. Okay, so it makes it very easy to use conservation of energy now for these dropping problems versus our constant acceleration equations. Now let me show you one more type of problem, and this is where something's like sliding down a hill. So let's say we have a frictionless plane. Now it's important that it's frictionless because I just said we were going to ignore the ideas of heat loss and friction so that we can conserve mechanical energy. Right, so if there's friction on this plane, then we've got to use our old school force equations or our constant acceleration equations. But for this, let's say we have an inclined plane, and let's say it's 2 meters high. And we have, a 2 kilogram, again, block, and it's going to fall to the very bottom of the hill. How fast is it going to be going when it gets to the bottom of the hill? Well, this is very easy for us to figure out because, again, we can just use conservation of energy. We know it has some gravitational potential energy because of its vertical height. So we're actually using this height. We're not going to be using the length of the incline. But if we were given the length of the incline and the angle, then we could easily figure out what this side is. It's going to be equal to the kinetic energy at the bottom. So again, we're just going to have mgh equals 1/2 mv squared. And we don't need any complicated like g sine of theta is equal to ma, nothing like that. So masses cancel again, and we get gravity is 10, the height is 2, 1/2 v squared. So 20 divided by 0.5 or multiplied 2, you get the square root of 40. Oops. Let's do. And I get 6.3. So V equals 6.3 meters per second. Okay, so those are some examples of using conservation of energy when we are dropping something or when it is sliding down a hill.